Hello everyone, welcome to the third part of the P block lecture series where I am covering every group of the P block elements in short and concise videos. And today we are going to cover group 15 elements. I have already uploaded it parts group 13 and group 14. Please look at those videos if you have to. And overall the response has been very positive and I would love to thank you guys for the same. I was not expecting such kind of response in just 3 days of posting, but yeah, that's enough bug. Let's begin. So let's talk about the group 15 elements. What are the group 15 elements? Again, I want you to tattoo this on your index finger, but make sure to hide it from the examiners at your exam center. The group 15 elements are nitrogen, phosphorus, arsenic, antimony, and bismuth. And they, for some reason, NCERT does not enough. What am I saying? NCERT does not mention enough information about most of the topics of group 15 elements. So hopefully this is a video which is on the shorter side. So let's begin. First of all, let's talk about abundance. The NCERT mentions that the gas N2, which is this covers. I mean, you must have studied it in earlier classes as well when you were like kids. The atmosphere contains 78% of nitrogen, which is a huge amount, like it is almost 4/5 of the total atmosphere. And this is quite obvious to say that nitrogen is the most abundant gas in the entire atmosphere, which is followed by oxygen and then other gases. Now let's talk about their behavior, like metal or non-metal. Metal or non-metal. So I want you to remember that nitrogen and phosphorus, they are non what what is this? 1 second, I used the wrong brush. Abe, I used the wrong brush here. Nitrogen and phosphorus are non-metals. Antimony is a metalloid, which means it shows properties of both metals and non-metals. And bismuth, Bi, is a metal. Now let's talk about the very small amount of information NCERT mentions about their obtaination. Let's just title this How to Obtain. And the NCERT only mentions 2 ores of nitrogen and does not mention any for the rest as far as I know. So the ores for nitrogen are NaNO3 and KNO3. Like basically you can say it's very easy to remember because there's sodium here, potassium here. They both are elements of the first group, and hence the nitrate ion has -1 charge, these are +1. So the overall compound is neutral and stable. So this is how they're formed. So NaNO3 is called chili, salt, petre, and close enough, KNO3 is called Indian, salt, petre. Now how do I remember this? Well, imagine a dining table. Na, you can use the analog of NaCl to remember, which is table salt. So imagine you are on a dining table and there's chili there, there's salt there. So that's how maybe you can remember this. And you remember when you text your father, they always reply with K or a thumbs up emoji. So that's how maybe you can remember Indian, because this is a habit of Indian fathers. And yeah, that's about it. I don't think you will have too many problems remembering these. Mains can ask questions, so just keep in mind. Now let's talk about the important part, which is the trends of group 15 elements. First trend is ionization enthalpy. Take a guess. What do you think will happen? Ionization enthalpy decreases as we go from top to bottom, and there is no exception with the which the NCERT mentions. The atomic radius increases top to bottom, and I think you can tell why these are so, because when the number of shells increases, like this is nucleus, this is first shell, this is second shell. I'm drawing only one electron in each shell for your understanding. This is third shell. So as you can see, when the number of shells keeps on increasing, the outermost electron strays further and further from the nucleus, and is hence less affected by the nuclear charge. So it is easier to just take this guy out of the nucleus and leave this guy with an extra charge. And this is also why the radius increases, because, well, the number of shells increases, so the radius does as well. So that was the explanation for both of these orders. The third thing I would like to mention is that the density. The density of group 15 elements increases as we go from top to bottom. You have to remember this. Then the fourth part is electronegativity. The electronegativity decreases top to bottom. You know how the normal electronegativity order goes. It decreases top to bottom and increases left to right. So this is just following that order. But you can say there is a half exception to this rule, where the electronegativity of antimony is more or less the same as that of bismuth. So you have to remember this as a fact. And the boiling point. Boiling point increases as you go from nitrogen to antimony. But there is an exception to this, which is that, if you're going from nitrogen to antimony, so antimony will have the highest boiling point if you look at the first four elements. And following the normal trend, you would expect bismuth to have an even higher boiling point. But actually, antimony's boiling point just so happens to be higher than that of bismuth's. So the overall order becomes like it increases from nitrogen to phosphorus to arsenic to antimony. But in the end, antimony takes the lead over bismuth, and hence this is the highest boiling point of the group 15 elements. And the melting point does not follow a order which is easily predictable. So just remember it, the order like AS, SB, BI, P, and N. Now I can give you two tricks to remember this. First thing, you can see that the alphabet begins with an A, so start this with A. And arsenic is AS, so S, S, B, B. So this is how you can remember the big guys. And after that, I don't think you will have trouble memorizing that phosphorus is greater than nitrogen. And the other way to remember this is, I won't say it loud, but, and this will help only if you know Hindi, but हाथ सब बिना पिए nacho. This will help you remember the melting point order of the group 15 elements. This, this, and this. I came up with this myself. See how much hard work I do for you guys. So drop a subscribe, man. It does not cost that much. It's literally free. But yeah, that's it for the trends of group 15 elements. Now let's talk about the physical properties. The physical properties of group 15 elements are, well, they'll be over in this page only. So let's first talk about the a point that the NCERT mentions is that the ionization enthalpy of group 15 elements is greater than that of the corresponding group for 14 elements. Now why is that? If you see the electron configuration of any group 15 elements, it will look like anything plus NS2 NP3. This is a group 15 element, and if you look at that of a group 14 element, it will be a corresponding group 14 element. It will be that same thing, but NS2 and NP2. So as you can probably tell that this is a half-filled p-block configuration. You know that the p orbital, it has 6 spaces for electrons, but here this is exactly filled. And as you know, our nature, like how things work at the atomic level, they appreciate symmetry a lot. So a half-filled configuration is a lot more stable than a non-half-filled configuration, and hence if something is stable, the nature of the object is to prevent you from taking away its stability, which is why the ionization enthalpy of the group 15th element will be much higher than that of the group 14 element, because the group 14 element lacks symmetry and this has symmetry. This was a point that the NCERT mentioned. I explained it for you. Now, all of the 5 elements exist in polyatomic state. I want you to remember this as a fact again. The NCERT mentions this as a separate line. All of them exist in polyatomic state, and all of the elements show allotropy. Now, what is allotropy? We covered it in the lecture we did for group 14 elements. The group allotropy is basically when one single element can exist in multiple crystal lattices. For example, if one element is exist in a cubical lattice where it is occupying one atom of the element is occupying each vertex of the cube, or maybe it is existing in a tetrahedral lattice where it is bounded to 4 more atoms simultaneously, and these are bounded to 4 more atoms, and this forms a big chain which is a lattice. The fun fact, this is the structure of diamond, and this is structure of a lot of elements, but I haven't studied solid state, so I don't know. Now all of them show allotropy except for N2. N2 does not show allotropy. And the last point which I would like to cover, all of them are solid except N2 again. You know, the second period elements show different properties in comparison to the rest of the elements of the group, and this is just a reflection of that. Now let's come to the last part of the lecture, which is chemical properties. What are the chemical properties of group 15 elements? So first of all, let's talk about what oxidation states are shown by them. So the oxidation states that can be shown are either +3, +5, or -3. Like, and nitrogen shows a lot more than just these, but these are the like group oxidation state you can say. And for example, like in NF3, the oxidation state of nitrogen is +3, but while in NH3 it is -3. So this just shows you the diversity that group 15 elements can show, and this is just a reflection of that again. So yeah. So first, obviously it follows the inert pair effect. The +3 oxidation state increases in stability down the group because the 2s electrons tend to become inert in chemical reactions and they do not like to be unpaired. So that is how the inert pair effect came to be. Now coming to the next point, nitrogen and phosphorus can also show all oxidation state from 1 through 4 with oxygen. Well, one point I forgot to mention about the inert pair effect, that as you know the stability of plus 3 increases down the group, and bismuth rarely, bismuth and plus 5 oxidation state, they are like, they hate each other. Bismuth hates to be in the plus 5 oxidation state, but there is only one exception to this, which is basically bismuth fluoride, BiF5, bismuth pentafluoride. This exists, which has the bismuth oxidation state as positive 5 and fluorine negative 1, so it's counterbalanced. And bismuth F5 is the only well characterized compound of bismuth which exists in the plus 5 oxidation state. And the NCERT mentions this, I just forgot to mention, so it hit me that I had missed something, so I just went and checked my source material, and yeah. Now, one thing very interesting to see is that nitrogen in first to fourth oxidation state can disproportionate. Now, what is disproportionation? You know, you have studied in redox reactions that basically disproportionation is okay, if an element is in, say, element X is in plus B oxidation state, and it breaks down into two compounds in which it is in plus A oxidation state and C oxidation state. So if B is intermediate of both of the oxidation states of plus A and plus C, like B lies in between of them, so we call this phenomena to be disproportionation, where one oxidation state breaks down into two oxidation states, which one of them is higher than it and one of them is lower than it, so the element can preserve stability. Now let's see an example of this. An example of this is that, say we have HNO2. This is the nitrite ion and this is the H plus attached to it, so it's an acid. So this thing has the oxidation state of nitrogen to be, what is the oxidation state? You know, oxygen shows -2, so this total is -4, this is +1. So nitrogen must be +3 in order for the compound to maintain neutrality. So here the oxidation state of nitrogen is +3. Now this can disproportionate into HNO3 plus NO, like 2 mole 3 moles of this can disproportionate into HNO3 plus 2NO plus H2. You don't have to remember the balancing for mains, just know that this happens. And here you can see that this was +3, but here the oxidation state of nitrogen is +5. How? Because hydrogen is +1 and the net oxidation state of all the oxygen atoms combined is -6. So this plus this should counterbalance the negative oxidation charge, which it does. So here oxidation state of nitrogen is +5, and in this guy, I guess it's called nitrous oxide, but I don't remember the IUPAC of inorganic compounds with. But what I can tell that this is a +2 oxidation state. So here you can see that it is going from +3 to two oxidation states, one of which is higher and the other one which is lower. So this is an example of a disproportionation, and that's what I wanted you to know. And even greater disproportionation ability is shown by phosphorus, and examples, and it usually disproportionates to like +5 or -3. So let's see examples of this. One example is that white phosphorus, which is P4. I'm not writing balance reactions. P4 can disproportionate into PH3 plus the hypophosphite ion. Now here, as you can see, P4 is in zero oxidation state, but here the oxidation state of P is -3. But here the oxidation state, how are we going to calculate the oxidation state of phosphorus? We know phosphorus plus 2 into the oxidation state of oxygen plus 2 into that of hydrogen must be equal to the net charge on the molecule. So P minus 4 plus 2 plus 1 is equal to 0. So minus 4 plus 3 is my -1, and that would mean that oxidation state of phosphorus is 1. And here you can see 0 breaks down into -3 and +1, and 0 is between those values, so this is of course a disproportionation reaction. And another example I want to show you is that H3PO3, you must have read this in chemical bonding, it can disproportionate into again phosphine PH3 plus orthophosphoric acid, which is H3PO4. Like this H3PO3, here the oxidation state of phosphorus is +3, and here the oxidation state of phosphorus is -3, while in this case the oxidation state of phosphorus is +5. So of course +3 is intermediate of -3 and +5. So this is an example of a disproportionation reaction. So we have just talked about the disproportionation of nitrogen and phosphorus. Let's move on to further points. The next point says that nitrogen, it's a second period element. Like, of course, no shit, nitrogen is a second period element. But what I want you to remember that in the general points we studied 2 lectures ago, the smaller elements, due to having lack of d orbitals, they can form p pi multiple bonds with each other. For example, say n triple bond n. So this is a very strong compound, and that perhaps explains its abundance in the atmosphere. It is so stable that it takes up 4/5 of the entire atmosphere. Right, and that just shows you how stable this is, because 3 bonds, why? They're very stable. And p pi bonding, of course, I just told you that. Now there is one point though. If we just talk about the n single bond, like this is a single bond, and then we talk about the phosphorus single bond, the phosphorus can accommodate its lone pair better because it is a bigger element, so higher dispersion of charge takes place. But nitrogen being small, these lone pairs interfere with the strength of the bond and they repel each other, which causes this bond to like extrapolate, and these just go further away. And as you know, this makes the bond weaker, and hence we have to come to the conclusion that phosphorus single bond is stronger than the nitrogen single bond. But JEE Mains 2025 asked a trick question on this. They asked you whether n, single bond is longer than the p, single bond. Now many people, myself included, like that time I obviously did not know inorganic chemistry, I was zero in it. So I just thought that there will be lone pair, so this must repel and this must get longer than the phosphorus single bond. And in chemical bonding, I had studied that bond length is inversely proportional to bond strength. So for the fact, I knew that this bond is weaker than this bond. So I thought n common bond will be longer, and I take that n common bond will be longer. But I was wrong. The phosphorus bond is longer than the n bond in terms of length. Now why is that despite this bond being stronger? Well, you know that this criteria applies only when you are comparing bonds between two similar elements. Like in one compound, I am comparing a bond between nitrogen and oxygen, and in other compound, I am comparing nitrogen versus oxygen. So here I can compare because the elements I am comparing are the same. But if I'm talking about two completely different compounds where the elements have different properties, so since phosphorus has a bigger shell and it has a larger atomic radius, the radius is defined as the contribution of an atom to the bond length. So this bond is actually longer than the n single bond, and simultaneously it is stronger than it as well. So this was a trick question which means asked, and a lot of people got it wrong, including myself. So I would like to teach this to you as a theory point. Not every long bond is weak. Now this is it about the chemical properties, like these properties you can expect when you are forming compounds with these elements. So let's now talk about the chemical reactivity. What is the chemical reactivity of these elements? For example, let's say if I talk about how do they react with hydrogen, it's pretty obvious. You just have to remember that they form MH3, like maybe NH3, PH3, BIH3. This is how they make the compounds, and these are hydrides. Okay, so you will have to remember some basic orders here, like stability of hydrides decreases from NH3 to BiH3. Like nitrogen is best able to take care of the three negative H ions, while this is not that good. And for the exact same reason, BiH3 is a good reducing agent. In fact, just as a consequence of this order, the reducing power increases top to bottom. Why so? Because this is stable. So why would it want to undergo a process which removes its stability? But this is rather unstable. So might as well do something which makes me more stable. So it can just give up one of its hydrogens, say bye bye, and this will attain an oxidation state which is more stable than its current oxidation state. But we don't have to dive into that because it's not in the NCERT. So, and if I talk about the basicity of these hydrides, like their ability to take in another H plus and basically just be basic, act like a base, so that character decreases top to bottom, which would mean that ammonia is more basic than phosphine, which is more basic than arsine, more basic than whatever this guy is called. But there's again a half exception to this, where the basicity of SbH3 is more or less greater than or equal to that of BiH3. Now this is a half exception because of this guy. It might be equal, we are not sure. So that was it about hydrogen's reactions with the group 15 elements. And now let's talk about oxygen. Basically oxides, right? We don't have, there was a topic in NCERT called oxides of nitrogen, but you don't have to study that in detail thanks to the revised syllabus. But you still have to remember some compounds with oxygen. So what do they make? They make either M2O3 or they make M2O5. As you can see, this is in a +3 oxidation state and this is in a +5 oxidation state. So of course there might be some references to the inert pair effect here. And the NCERT mentions that E2O5 is more acidic. Remember this as a fact. And if we talk about E2O3, which has like compounds like N2O3, P2O3, you get the point, right? So if I talk about this, NCERT mentions some points separately about just E2O3, where if I put in nitrogen and phosphorus, those oxides are acidic. If I put arsenic or antimony, those oxides are amphoteric. And if I put in bismuth, that oxide is basic. So only for E2O3 you have to remember this order. And just a separate point, just remember that NO is a neutral oxide. So that was it about oxygen and oxides. And I think the last part we have to study is about halogens. With halogen they make NX3 or NX5. Why have I written N? Just write M, right? Because M is already an element. So MX3 of course has plus 3 oxidation state, MX5 has plus 5 oxidation state. And of course, as per Fajan's rules, the EX5 is more covalent. Now don't make me explain this to you again, but just for your first timers, I'll do it again. If there is an anion here and there is a cation, now what happens is if the electron cloud of the anion gets pulled by that of the cation, and if the pulling is of great extent, what happens is this bond gets more covalent character. So this is increase in covalent character. So there are some factors which this depends on. For example, the oxidation state of the cation. The greater this positive charge, the greater is its pulling power. Like that's an obvious thing. If a charge is greater in magnitude, it will have better pulling power than a charge which is in smaller magnitude. So there's that. And in EX5, this charge is positive 5. So of course in positive 5 state, it will be good at pulling the anion cloud as compared to the plus 3 oxidation state. So this gets more covalent. So this was an explanation of why EX5 is more covalent. And another point is that even EX3 is covalent. But of course not to that extent of EX5, but EX3 is also covalent. But there is an exception to this. Of course, there is always an exception. Trying to study inorganic chemistry without exceptions is like going into the ocean and expecting there to be no salt. And there is BIF3, which is ionic. Now, why is that? BIF3 is ionic because fluorine is an extremely small anion. It is one of the smallest anions. So, no matter how good the cation is, like if this has plus this much charge, and this is really good at pulling the electron cloud. But if there is no electron cloud to be pulled, you can have charges as high as C plus 2, 2, 2, 3, 6, 7. Yeah, that just won't work because there is no electron cloud to be pulled. So, BiF3 is an ionic salt. And one last thing, if E is equal to nitrogen here, then only NF3 exists. NCl3, NBr3, Ni3. No, they don't exist. Why is that? Because of course these are bigger anions and they are hard to accommodate around the nitrogen atoms, and only fluorine can take care of nitrogen in its third oxidation state. And I guess that's about it. This was the entire group 15 elements covered from 0 to hero in one shot. And yeah, thank you for watching. Share if you want, and goodbye.